Physical properties of transition elements. As transition elements are metals, they show all the characteristic properties of metals, like they are hard, have high tensile strength, good conductors of heat and electricity, they are less volatile, ductile, malleable, good high tensile strength, means they show all the properties of metal. They have high melting and boiling point. This melting point and boiling point depends on melting point and boiling point of a metal depends on the strength of, what does it depends on? Strength of the bonding, right? Strength of metallic bonding present in transition metals. Stronger the bond, higher the melting and boiling point. This transition metals have strong interatomic metallic bonding. This is due to, in the case of transition element, in addition to the outer s electron, inner d electrons also take part in bonding. The more the number of electrons that take part in bonding, stronger the metallic bonding, higher the melting point. So the strength of metallic bonding depends on number of electrons that participate in bonding. Generally, the number of unpaired electrons are mostly involved in bonding. So as the number of unpaired electrons increases, means the number of unpaired electrons that are involved in metallic bonding increases, strength of the metallic bonding also increases. As the strength of bond increases, melting point and boiling point of these metals increases. Because in transition elements, more number of electrons involved in metallic bonding, their melting point is generally very high. Transition elements have high melting and boiling point due to stronger interatomic metallic bonding, which is due to more number of participation of more number of electrons in bonding. Let us explain taking the example of 3D series elements. 3D series starts with scandium, atomic number 21, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, the last member zinc. Atomic number 22, 23 for vanadium, 24, 25, 26, 27, 28, 29, 30. Let's write the configuration, the electronic configuration of 3D series elements. Scandium, after argon 18, we have after argon 18, it's 4s2, 3d1 for scandium. For titanium, 4s2 after 3d2. Vanadium, 3d3, 4s2. For chromium, an exceptional configuration, we expect 3d4, 4s2, but actual configuration of chromium is 3d5, 4s1, because in order to attain the extra stability of 3d5 configuration, one of the 4s electron shift to 3d, because 3d and 4s have very close energies. Electron can jump from 4s to 3d. So in case if there is a possibility of attaining extra stability of 3d5 configuration, 4s electron undergo transition into 3d orbital. Manganese, the configuration is 3d5, 4s2. Iron 3d6, 4s2. For cobalt 3d7, 4s2. Nickel 3d8, and for copper we expect 3d9, 4s2 configuration, but actual configuration of copper is not this one. One of the 4s electron shift from here to here. Why? To attain the extra stability of 3d10, completely filled electronic configuration. So this is not the actual configuration of copper. Actual configuration of copper is 3d10, 4s1. Now zinc 3d10, 4s2 is the electronic configuration. As you can see here, the electrons are filled in penultimate diatomic orbital, not in the valence shell. Electrons are filled in 3D atomic orbital, the inner 3D atomic orbital. And this 3D orbitals are also involved in bonding. Along with the outer s electron, 3D electrons are also involved in interatomic metallic bonding. That's why these elements have strong metallic bonding and they have high melting and boiling point. So let's study how the melting point and boiling point vary across the 3D series. As you can see here, I told the melting point depends on number of unpaired electrons. How many unpaired electrons are there in scandium? With the 3D1 configuration, it contains only one unpaired electron, right? Titanium contains 3D2, means 2 unpaired electron. Vanadium, 3 unpaired electron. Chromium, there are 5 unpaired electron in 3D, 1 unpaired electron in 4s. So total 6 unpaired electrons are present. Manganese, it contains 5 unpaired electron, 3D5. Iron, what happened? There are 6 electrons. The 6th electron starts pairing in 3D, right? So due to pairing, number of unpaired electron will be less. It contains how many unpaired electron? 4. Cobalt, 3D7, 3 unpaired electron. Nickel, because pairing started, the added electrons start pairing. So 3D8 means only 2 unpaired electron. For copper, 1 unpaired electron is present in not in 3D but in the 4s atomic orbital. Zinc contains fully filled 3D and 4s configuration, means no unpaired electron. So as we already discussed, as the number of unpaired electrons increases, metallic bonding becomes stronger, melting point increases. So initially from scandium to chromium, what happens? Number of unpaired electrons increases, right? Number of unpaired electron increases means strength of the metallic bonding also increases, melting point also increases, correct? Initially from scandium to chromium, the metallic bonding becomes stronger. Why? Because number of unpaired electron increases. More number of electron take part in bonding means metallic bonding is stronger, melting point increases. And from chromium towards the right end, what happens to the number of unpaired electron? Number of unpaired electron decreases, hence metallic bonding becomes weaker, hence melting point also decreases. Melting point initially increases, reaches a maximum value. Maximum or highest melting point corresponds to chromium. Why chromium has highest melting point? Because of more number of unpaired electron. It contains 6 unpaired electron, so stronger metallic bonding, its melting point is maximum among 3D transition series. And after chromium, what happens? Number of unpaired electron decreases and hence melting point also decreases because the metallic bonding gets weaker with a lesser number of electrons taking part in bonding. But here, in the case of manganese show an abnormally low melting point. In the case of manganese also like chromium, there are 5 unpaired d electron. Manganese, the configuration is 3D5 4s2. There are 5 unpaired electrons. So manganese also we expect a higher melting point, but manganese show an anomalous behavior. It has abnormally low melting point. Manganese has abnormally low melting point. This different behavior of manganese is explained because of its 3D5 4s2 configuration. As you can see here, 3D5 means half-filled diatomic orbital, highly stable. 4s2, 4s atomic orbital with 2 means 4s is completely filled. Means 4s atomic orbital also highly stable. So because of the stable arrangement of electron, stable electronic configuration in 3D and 4s, it has these electrons has less energy. They are highly stable means their energy is very less. These electrons are strongly bonded to the nucleus. These electrons are tightly bound to the nucleus. So these are not involved in metallic bonding. So metallic bonding in manganese is weaker due to the stable arrangement of 3D5 and 4s2. Similarly, in the for 4D series also. In the 4D series also, 4D series, just below manganese there comes technetium. Technetium has the electronic configuration 4D5 5s2. 4D5 5s2. Here also stabler, same story. Means stable electronic configuration, half filled and completely filled. So these energy is very less. These electrons are tightly attracted, strongly attracted by the nucleus. So these electrons are not involved in metallic bonding, weak metallic bonding. So their melting point very low. So manganese and technetium show abnormally low melting point because of their stable electronic configuration. Metallic bond is very weak. They have low melting point. And when we compare the melting point of 3D transition series with that of 4D and 5D. 4D and 5D have higher melting point than 3D. Because down the group, as the size increases, metallic bonding gets stronger. So their melting and boiling point also increases. 3D has smaller melting point than 4D, which has smaller melting point than 5D.